Hi everyone. So today we're going to be looking at displaying and comparing quantitative data, and in that topic we're going to look exactly at how do we describe and compare distributions. Okay, so how do we describe and compare distributions? So the first one we're going to look at is called the shapes of distributions. All right. And before we start with some of these problems, I'm just going to do like a really quick review of different shapes of distributions. So I'm going to refer to a very uh, great, it's a review of shapes of distributions in mathbitsnotebook.com. All right, so mathbitsnotebook.com. And they've made a great little outline of the different shapes of distributions. So basically, when we graph data, um, we basically arrange how the points are distributed throughout the set, right? We arrange how the data set is distributed, and we frequently use things like a histogram, right? And in using these graphical representations of our data, we can kind of look at it and see the spread. Okay, what's the spread of this data? And when we talk about spread, we also look at what's called dispersion, variability, and scatter of the data. We're going to get into that in much more detail as we go. But for now, we just want a general idea of this thing called spread. Okay, spread may be stretched, covering a wide range, or squeezed, covering a narrower range, right? So your data is very compact, then you're going to have a very narrow range. If your data is very spread out, then it's gonna be stretched. All right, so the shapes of distributions. Okay, well, how do we describe the shapes? Well, in a few ways. We could describe it with the number of peaks, how many peaks there are, by possession of symmetry, tendency to skew, and or uniformity. All right, distributions that are skewed have more points plotted on one side of the graph than on the other. Okay, so this idea of skew is going to come into importance as we do the problems. Now here, peaks. So the first thing we're looking at are peaks. Peaks. So we have this little sample distribution, right, a sample histogram, and we can clearly see that there are two clearly defined peaks in this distribution. So we're saying that we know that when we studied our statistics way back, we learned about mean, median, and mode, correct? Mean, median, and mode. And we know that the mode represents the number that appears the most, correct? That was way back, right, in grammar school. Well, same way we can look at this distribution, right, this histogram, and we can say, well, hold on, there seems to be two clear peaks for this distribution, right? This bar, these two bars here, these two buckets, right, or bins, it seems that they are very clearly greater than all of the other buckets. So we can say that this thing has two maximum peaks. And if we want to use the term mode, right, the number that appears the most, we can say that, hey, the data that appears from 11 to 20 and from 31 to 40, they appear the most. So since there's two, we can call this a bimodal. This is a bimodal distribution. If we only had one peak, we would call that a unimodal distribution right here. So one clear peak is unimodal, and two clear peaks is called bimodal. Now, this idea of a single peak at the center. What if there was one single peak at the center of this distribution? Well, we can call that bell-shaped. Call that a bell-shaped distribution, right? Or what's known as a normal distribution, right? It's a normal curve. So imagine one peak right in the middle of the data set. So then everything else is below that. So we can kind of fit a bell through those bars, through those buckets. Okay? Now, let's compare the shapes of distributions here. Okay, we have histograms, dot plots, and box plots, otherwise known as box and whisker plots, correct? And you've seen this probably in either grammar school or in junior high school. All right, And all three are ways of representing quantitative data, a distribution of data, right? So here we have a bell-shaped curve, right? We said one unimodal. This is a unimodal distribution. The middle, right? The center bin seems to be the highest. So it looks like it's sort of an inverted U, right? An inverted quadratic, correct? So this we can call a bell-shaped curve, which is symmetric because on both sides of the symmetry, it's both sides of the middle bin, it seems to be a mirror reflection, right? Mirror image of each other. Here, when we do it with a dot plot, again, the same idea, right? The middle of your distribution is the highest, you have the most, right? It's unimodal, and then both sides seem to be mirror images, right? Now, it doesn't always necessarily have to be a perfect mirror image to be considered a bell-shaped curve, all right? It's nothing in life is always perfect like this, but this is just an example. And here, again, the same idea of a symmetric distribution, right? We have, if you remember your box and whiskers, remember that this line inside the box is the median, correct? And we know that these ends here, they represent the maximum and the minimum of your data. So that's the range of your data. Here's your minimum value. Here's the maximum value. We know that these whiskers here, right, that extend out, they represent a quarter of your data each. So a quarter, right, a quarter. And then these two parts of the box, right, the left side of the box and the right side of the box represent quarters of your data. So basically, a quarter of your data is here in this whisker. A quarter from this point. This is the what is it? The first quartile, right? First quartile to the median, and the median is really the second quartile, right? So a quarter of your data is in here. A quarter of your data is from the median to the third quartile, which is the edge of the box here, okay? And then the rest, okay? And again, these points here, the first quartile value and the third quartile value, are basically the medians, right? The medians of the lower half of your data and the upper half of your data. So again, if you split this into halves, so the bottom half would be from the median down to the min, and the upper half would be from the median all the way up to your max. And this is just the median of the upper half, and this is the median of your lower half. Okay? So everything looks nice and symmetric. We keep going here. Now we could have an inverted symmetry, right? Instead of a bell shape, we could have an inverted bell, a real quadratic type of situation, where this is also symmetric, but it's U-shaped, right? So again, here, this is symmetric, it's U. And here we can tell that this is U because the majority, if you look here, this can represent a U-shaped symmetric data. Please take a look at the difference between the two box plots, all right? We're going to call it box plots, not box and whisker. Now, skewed. What does skewed mean? Skewed means that if you look at this distribution, it appears that there are fewer data values on the right side of the distribution on the left, right? The majority of your data is on the left. Therefore, it seems like it's sort of tailing off to the right. Your distribution kind of tails off to the right. That's why we call this a right tail. Okay? Fewer data values are at the tail. So if your right side of the distribution it seems to be less or lower, then we call this a right tail. Okay? And we call it skewed right. And the other way, here, if most of your data is to the right and it seems to tail off to the left, we call that skewed left or left-tailed. So this is right-tailed and this is left-tailed. It sort of looks like there's a tail, right? It sort of looks like, imagine if this is like a cat or a dog, it looks like the tail is on the right side. And likewise, if the dog or the cat is here, then it seems like its tail is to the left. Okay? Skewed left, skewed right. Same idea with our dot plots, right? Skewed right, majority of your data is to the left, so it's skewed right. Majority of your data is to the right, so it's skewed left. And this is how it would look like using the box plots. Again, majority of your data, this is 3/4 of your data is here, from the minimum to that third quartile. Only 1/4 of your data is on the right side. Likewise here, 3/4 of your data is to the right, and only 1/4 of your data is to the left. So therefore, we call this a skewed left condition, and we call this a skewed right condition. Okay? So now, finally, in this last distribution, we call this a uniform distribution because if we look at the bins, they are all of the same height. When we have uniformity in the distribution, we call that uniform. So this is what it would look like using a histogram, here using a dot plot, and here using a box plot. Okay? All right, so I think that's more than enough for you guys to be able to do the problems. So let's go and take a look at some of them. Okay, first problem, what is the shape of the distribution shown below? So we have two choices. Take a look at this box plot, right? Again, this is the min, that's the max, right? Here's the first quartile or the median of the lower half of your data. Here's your median value, and here is the median of your upper half of your data, otherwise known as the third quartile. So 1/4, 1/4, 1/4, and then 1/4, right? So is this distribution symmetrical or is it not symmetrical? Well, clearly we can see that this is about the halfway point here, right? Between the min and the max, so halfway is here, but it looks like 3/4 of your data is to the right of the halfway point, and only 1/4 is to the left, correct? So this would be an example of a non-symmetrical distribution. Okay, let's take a look at another one. What is the shape of the distribution shown below? So if you look at the distribution here, right? Clearly we can see that the majority of your data is to the left side, correct? And we see some data trailing off or tailing off to the right. Okay, so remember, as we discussed, this deals with the age of each of Gabriella's shirts. So it definitely looks like this distribution is being skewed to the right, correct? Remember, right, skewed right means tail right. So the distribution is skewed to the right. Okay, good. Let's take a look at another one. What is the shape of the distribution shown below? So here we have the distribution, right? We have all the bins, and you can see that even though it's not perfectly symmetric, if you were to fit a curve, right? A curve through the middle of each of these bins, it would look pretty symmetric, right? So here, even though, like I said, it's not perfect, it's not pushed to the left or the right. We don't have a majority of the data on either the right or left sides. It looks like we have a unimodal distribution going right through the middle, and it looks like it's sort of evenly placed onto the left and to the right side of your data. So therefore, we can call this distribution approximately symmetrical. Okay, and then finally, let's take a look at the last one. What is the shape? Here again, it looks like, given this box plot, if we were to split this in half, okay, halfway point would be about 45 here. And we can clearly see that 3/4 of your data is to the left side of this halfway point. Only 1/4 of it is to the right. So therefore, this again is an example of a non-symmetrical distribution. Okay. And again, a symmetrical distribution would have to have this box right somewhere in the middle between the min and the max, and your median should be around the middle. Okay? All right, guys? All right, thank you.